So here's the next couple of examples here with integrating exponentials. And you can kind of see with 5 and 6 here, we're sort of integrating an exponential base a. So again, the integral of an exponential is itself, you just have an extra coefficient involved. Now for the derivative, you're multiplying it by the natural log of a. So we're going to do the opposite when we integrate. We're going to divide by the natural log of a. So I'm going to utilize that here, and kind of starting out the same way. You see that subtraction sign in here. You are allowed to handle these guys separately. I can say, well, let me work on the integral of 2 to the x dx, and then let me work on the integral of x squared. You're allowed to do these things term by term or piece by piece. So I'm going to go with my antiderivatives here. Again, the integral of an exponential is itself. I'm just going to have this extra coefficient of 1 over the natural log of 2. And then I will multiply it by itself, which is 2 to the x. That is your antiderivative. And then moving on over here, again, this is your standard power rule. This looks like a pretty good antiderivative. If you would like to write it in a different way, you certainly can. You could write 2 to the x over natural log of 2. That's the same thing going on there. And if you wanted, you could write 1/3 x to the third plus c. Okay, they're equally awesome. It's not like I prefer one over the other. It's just whatever makes sense to you on writing this. Okay, now when I move over to problem number 6, you can see that, well, this is not term by term. I do not have a quotient rule for integration here. I cannot just simply do the antiderivative of the numerator over the antiderivative of the denominator. That's the whole point. I have to use that other strategy of a u substitution. I see something other than x going on up there in that power. That's where you go and look for your u substitutions with exponential functions in integration. That's your best spot to look. So that's what I'm going to let u equal. I'm going to let u equal the square root of x, that square root of x, not this one down here. Now, what I'm going to do is rewrite the square root of x as 1/2, because it's a lot easier for me to see that rational exponent than seeing it in radical form. Okay, so there's my derivative, there's my follow through, as I normally say, and I'm going to do a little bit of work on here. That means this, right? X to the negative 1/2 means drop it down to the denominator. I put it in radical form there just because. And then I'm going to multiply this through. I want to isolate for dx. So 2 root x du is my legal swap for dx. So that was a lot of kind of lines of work there, but that'll get me going. Now, I'm going to translate this integral into my u substitution. So remember, I had this exponential base 6. It was the exponent that I let equal u. And I didn't do anything down there with that square root of x that was hanging out. But what I do have in place of dx is I have 2 square root of x du. And this is now perfect because those root x's totally cancel out. And I want to be careful at this step, that there's a coefficient of 2. I'm going to throw that outside the integral. And I'm integrating 6 to the u du. What I don't want you to do is anything weird like multiply the 2 and the 6 and say, oh no, my base is 12. That can't happen. Your base is 6. You can't mess with that. Almost like maybe parentheses there. Like, don't invade the base of that exponential. What I will do now is come up with my antiderivative, which is, 1 over the natural log of 6, 6 to the u plus c. I'm just going to carry the 2 down because it's just a coefficient. So I'm going to round this out just by kind of, I don't know, maybe collapsing those 2 coefficients together, and then of course switching back to the x variable because that was the variable you were presented with in this problem. Okay. Now, if this makes it look weird for you, again, go ahead and take the derivative of this and you should end up with your original integrand as your answer. Okay, so here we have two more questions, just handling some definite integrals here, getting back into that fundamental theorem of calculus. Most of our examples are indefinite because I want to practice as many rules as possible, but here we have a definite integral, which means my answer is going to be a number, a value of some kind. And so there's two ways of doing, these two problems as a definite integral. In both cases, we're going to need a u substitution. And so if I focus on problem number 7, I'm going to look right up there because that exponent there is not just plain old x. There's some other function going on there. So that's going to be the u substitution that I'm going to get started with. I'm going to go ahead and do the follow through, which is fancy for take the derivative of both sides. And I'm going to solve this thing for dx by itself. Okay. So one way of handling a definite integral with u substitution is just to kind of like lay off your limits of integration, meaning I'm not going to write them in. I'm going to pretend this is an indefinite integral, and I'm going to go through all of my swaps. Instead of negative x squared, I'm replacing it with u. Instead of dx, I have du over negative 2x. And you can kind of see the awesomeness here that these do in fact cross out. The x and the x, those guys are gone. And so you can get back into, well, I'm just going to come up with my antiderivative. Notice I do not have the limits of integration written in here. I shouldn't, because those limits of integration belong to the x variable. They do not belong to the u variable. So I'm going to kind of leave them off. I'm going to come up with my antiderivative, which is, well, negative 1/2 is just a coefficient, e to the u. Now normally I would do a plus c, but what I'm going to do is switch back to the x variable. It's at this moment that you're allowed to use those limits of integration from 0 to 1. Okay, so I kind of left them off, they were absent here, and then I bring them in right at the moment that I actually convert to the x variable. And now we'll use that fundamental theorem of calculus, which I'm going to go ahead and plug in a 1 in for x into that expression. Then I'm going to subtract, and now I'm going to plug a 0 in for x. And so here is my answer, which looks pretty good, but I'm going to switch that e to the negative 1. I'm going to switch it so there's no negative exponents. That would be 1 over 2e. So this is your final numerical answer for the value of this definite integral. Okay, so again, that's one way of handling a definite integral with u substitution, is you just kind of leave those limits of integration off, that 0 and 1, because they only belong to the x variable. You bring them in right at the moment you're allowed to. You would not be allowed to import them here. Okay, so that's one way of handling it. Let me go up, and I'm going to handle this one in a different way. If you want, you can do what's known as a complete change of variables. And so I'll show you what I mean by that here. So let's address this one. This is, again, it's an exponential. The type font here doesn't look great, but this is 3, base 3 with a power of x over 4. Okay, that's my power in here. So that is what I'm going to say is something different than just plain old x. That is the exponent on 3. So I'm going to do that. I'm going to let u equal x over 4. And everything about this is the same. It's using the strategy of a u substitution. I'm going to take the derivative, nothing different here. I'm going to solve this so it says dx equals, so I'm going to multiply by 4 on both sides. So now I have my full switch there. And I am going to switch this over. I'm going to convert this into what I've got. Well, I have the integral, and I've got 3 to the power of u, because that's what I'm switching to. And then in place of dx, I'm going to do 4 du. Okay, now, instead of ignoring the limits of integration, you can kind of see you've just transformed everything from the x variable to the u variable. So let's go ahead and get limits of integration here that actually belong to the u variable. So let me show you how to do that. Your original limits of integration here, just that lower limit of integration, that's x equals negative 4. So I'm going to come out here. If x equals negative 4, then let's solve what u is. Remember, u is x over 4. So that means your lower limit of integration, if I switch to the u variable, instead of writing negative 4, that's the x value of that lower limit of integration. If I just kind of use the substitution that I had decided upon and throw that negative 4 in, well, now my lower limit of integration is negative 1. I'm going to do the same thing on the upper limit of integration. There's my upper limit of integration. Well, there I can clearly see x is 4. Well, then I can convert that over to u too. Then u equals 4 divided by 4, which is 1. So here's another way of addressing it. This is what's called a complete change of variables. And I like to address both of these strategies because you've all had different Calc 1 instructors where some might always insist on the complete change of variables. Some might do this kind of, I don't know, ignoring strategy and then bringing them back in when appropriate. Both are fine, but I want to address both of those issues. Okay, so now that I have completely transformed my integral from the x variable to the u variable, I'm ready to actually get my antiderivatives and work on it. And so, again, the antiderivative of 3 to the u is going to be 3 to the u. You're just going to have an extra coefficient of 1 over the natural log of 3. Now, that 4 is still there. It's just kind of a coefficient that's coming along for the ride here. And you already have this worked out so that your limits of integration are ready to go here. You have them in terms of u, so I'm going to apply them right now. This is a lot faster than the previous version. Okay, so now I'm going to use my fundamental theorem of calculus. I'm actually going to come down here so I have enough room to do this. So I'm going to first plug in the 1, and then I'll plug in the -1. And that looks like a pretty good answer. I'm going to rearrange it a little bit. Math people sometimes don't want negative exponents in our answer. So I'm just going to kind of congeal this together. That's 12 in the numerator, natural log of 3 in the denominator. And here, 4 in the numerator, and that 3 to the -1 comes down. And that looks like a good answer. Okay. Just for the sake of it, just to mention this, I don't know if this would be important to you, but like let's say, I don't know, you have a multiple choice question and that is not a possible answer. Let's think about our rules of exponents. I could rewrite that denominator as the natural log of 27. Pretty wild, but that's the same thing. Remember that property that that coefficient can kind of come in front as that power. That's another version of an awesome answer.